Right. So we have our next question. Yeah, next method of mixtures question. So a metal block of mass 3 kilogram is heated until its temperature rises to 140 degrees. Now the metal is then placed into a container of water and stirred until the temperature of the water stops rising. The mass of the water is 10 kilogram and its temperature increases from 15 degrees Celsius to 20 degrees Celsius. Now, if the specific heat capacity of the water is 4200 joule per kilogram per Kelvin, what is the specific heat capacity of the metal? Alright, so this is our next method of mixtures type question. So again, in the before diagram here, a diagram always helps with this. Right, so in the before diagram here, we have a beaker. Right, it has water in it. Right, now the initial water of this could be T1. That could be, let's say, um, its temperature increases from 15 degrees Celsius to 20. Right, so we do have to put T1 on thing. Well, actually, let me put the T1. So we have 15 degrees Celsius here, right? And we have the hot metal block up here. Now this metal block has a temperature, let me say that is T2. Let's say metal block of mass that is heated until it rises. So this is the maximum temperature of the metal block, 140 degrees Celsius. The mass of the block, I'll put MB, that will be equal to 3 kilogram. Did they give us the mass of the water? Yes, they say the mass of the water, which is M, is actually equal to 10 kilogram. Right? So now let me say this is the after diagram here now. So we have the container of water here now. Right? So what happens is we have the metal block inside here now. Right? The new temperature, let's see, the temperature of the water rises from 15 degrees Celsius to 20 degrees Celsius. So the new temperature here will be 20 degrees Celsius. We could call this T3. Right? With the specific heat capacity of the metal. So during method of mixtures, we have to apply this formula here. That is, let's see, we should see the heat energy gained by the water will be equal to the heat energy lost by the metal. Right? So heat energy gained by water is equal to heat energy loss from, will be dealing with our block. Right? I got put loss from the block. Right? So the heat energy gained by the water, that will be denoted by mass of the water multiplied by the specific heat capacity of the water multiplied by the change in temperature of the water. That is equal to the heat energy lost from the metal block. Will be the mass of the metal block, output MB, multiplied by the specific heat capacity of the block multiplied by the change in temperature of the block. Right? Um, so delta TW, remember it rise in temperature from 15 degrees Celsius to 20, so it could be 20 minus 15. So this could be 5 degrees Celsius. This is delta TW. Right? Now delta TB would be, well, you have a decrease in temperature. Remember they're both going to remain at the same temperature, which is this T3 here. So you're changing from 140 degrees Celsius, you're decreasing to 20 degrees. So the change in temperature for the block will be 100 and, wait, was 140? Yeah, 140 minus 20. this could give you 120. So I find my change in temperature for the block. Right? Nice. Degrees Celsius. Do I know the mass of the water? Yes, I do. The mass of the water was given to be 10 kilogram. Right? The mass of the block, we know that was given to be 3 kilogram. The specific capacity of the water, um, we know that to be 4200. I don't put the unit, but I could put the unit joule kilogram per Kelvin. We don't know the specific capacity of the metal block. This is CB. This is what we don't know. We had to solve for that. So what we could do, we could plug in everything now into the formula here, into this equation up here, baryonic, right? Instead of MW, I'm putting 10. Instead of CW, I'm putting 4200. Instead of delta TW, I'm putting 5. That is equal to the mass, which is 3 kilogram, multiplied by the specific capacity of the block, which is CB. We know is as well, just put CB. Multiply, that should be common CB, small CB. This is specific heat capacity, right? Multiply by the change in temperature, which is 3. No, 120. 120. Right? Don't want to make any errors with calculation. So I could just flip this. I could say, 3 by 120 will be 360 multiplied by the specific heat capacity of the block. That will therefore be equal to 10 by 4200 by 5, which should be 210,000. 210,000. That is the energy for the energy gained by the water. That's what I'll be in joule. The specific heat capacity. No, I don't need to put in the unit yet. I could just remove that unit for now. And the specific heat capacity is equal to 210,000 divided by 360. Right? This should be equal, specific heat capacity of the block should be equal to divided by 360. I'm getting 583.3, and this will be joule per kilogram per Kelvin. So if you have the incorrect unit, you're going to lose a mark, yeah? So remember, specific heat capacity is equal to the heat energy divided by the mass multiplied by the change in temperature. Just plug in your unit for energy, which is joules all over kilogram per degree Celsius. Be J per kg per degree Celsius, right? The minus 1, right? Or it could per Kelvin, same thing, right? So this is my answer here. Understand the solution here? Right? So that's that. Now determining the specific capacity of liquids, method of mixtures. So you had thermal energy gained by the water is equal to thermal energy lost by the liquid. That is for two liquids. So M subscript L, C subscript L, that is for the liquid, right? And M subscript W, C subscript W, that is for water. So you're mixing two liquids basically. You heat a liquid, then you place it in a cup of cool water, and then you measure the temperature. Change again, you use this formula basically here. You make Cl the subject of the formula, just like what we did, and you will get the specific heat capacity of a liquid. Simple, right? You have determining the specific heat capacity of metals using electrical method. Very important to know too. So you can use electrical energy is equal to the increase in thermal energy of the block. We know energy increase of the block will be mc delta T. Now delta T is T2 minus T1. That is how they get this here. But how they get VIT? Well, that is the formula for power for electrical energy. Right? That's the formula for electrical energy. Volts by the current by the time. right? So this is the setup of it. Most likely you wouldn't be doing this one in school, but it's still important to know this equation, right? Insulating material to reduce heat loss to the environment, heating element surrounded by oil. Why is it surrounded by oil? Oil placed around the thermometer and heater improves conduction with the block, conduction of the heat energy. The block is surrounded by an insulating material to reduce outward conduction or to reduce heat loss to the environment. A polished silver jacket foil paper surrounds the insulator to reduce radiation to the air. Right? You have the metal block, you have polished outer jacket, basically you have the circuit here, the voltage, the current, rheostat, switch, battery, well, more like a cell, right? But when we get a problem like this, we'll go to the calculation. For now, just to know the experiment. This is an experiment you would probably do in chemistry and physics. That is to determine the melting point of paraffin, wax, or stearic acid. Right? Specific latent heat is the energy used to change the state of a substance. State means solid to liquid or liquid to gas. Or vice versa. You could say liquid to solid or gas to liquid. Same thing. Right? But that is specific latent heat. The energy used to change the state of a substance. Demonstrating that the temperature remains constant during a phase change of paraffin wax. What does constant mean? It means it not changing. As we can see in this graph here, yeah, temperature versus time. Notice this is a flat line here. This means constant temperature. And if we do in chemistry, this will be like the first topic in chemistry, states of matter, right? So you do have any change in temperature when you have a change in state, right? You have melting going on here, melting taking place here. So what we gonna do is we gonna have the retort stand here. We gonna clamp the paraffin wax inside this test tube and put it in a hot beaker of water. Supply heat with a Bunsen burner or something, right? And you gonna melt the wax. Then you gonna take it out of this beaker of water and you gonna allow it to cool. And you gonna record the temperature every 30 seconds or every minute, whatever the case may be. And you gonna realize that the temperature not changing for a specific amount of time. That is when you have a change in state. It changing back from the liquid to the solid, solidifying, right? Melting point, um, basically would represent that, right? Melting point, freezing point, say basically almost like the same thing. So expected cooling curve. This is what you get expect in the lab, something like this. It wouldn't be a perfect graph. So when the liquid is cooled or the paraffin wax is cooled, the particles lose kinetic energy. And my kinetic energy is a half mv squared. If you're losing velocity, you're losing kinetic energy, it's moving less. Now the temperature falls. The particles become attracted to each other to form the solid state. Energy is released and the liquid turns to solid at 69 degrees Celsius. Temperature is constant. Here, T is constant, right? You have a change in state, you call that melting point, 69 degrees Celsius. When a solid is cool, the particles lose more energy. The temperature just falls, right? Because if you cool it more, it has no other state of form, right? You reduce it from liquid to solid, you can't form anything else after that. Good. Heat it back and form back the liquid, however. Right? So defining specific latent heat of fusion and vaporization. So fusion is LF, vaporization is LV. So the specific latent heat of fusion, LF, is the energy required to change 1 kilogram of a solid into liquid without a change in temperature. So T is constant. So right away you should know that you will only use formula relating to fusion and vaporization if the temperature is not changing, right? So specific latent heat of vaporization, LV, is the energy required to change 1 kilogram of the liquid into a gas without a change in temperature. This is the value for ice. Specific latent heat of fusion of ice. This is the value for water. Specific latent heat of vaporization of water. Very important. But it is normally given these values, but it's still important to familiarize yourself with. Right? And then had a heating curve here. So we just went through a cooling curve, now we're going through a heating curve. So this is very important to note because this graph here telling you which formulas you would be using at different stages, right? In heating a substance. So let me say you start off with ice. Let me say this temperature here is like negative 10 degrees Celsius. And you heat it. Let me say here with M dot P, the melting point. Let me say here is 0 degrees Celsius. Why did I put 0 degrees Celsius there? Because that is the temperature at which ice will melt and turn into liquid water. So here gonna be liquid water. Here gonna be you're changing the liquid water to steam. So here gonna be like 100 degrees Celsius. You have boiling taking place. Hence you have BP there, boiling point. MP melting point. So over here you have a change in temperature because remember this could be like T2, this could be like T1. So you have a change in temperature. But over here is still T2. So you do have a change in temperature when this flat line here. So here you could say this is T3. Over here, at this time you will also have T3. So you do have a change in temperature there for this flat line. But from T2 to T3 you have a change in temperature, so you can use MC delta T. Whenever you have a change in temperature, you can use MC delta T. When you do have a change in temperature, you can use ML, mass by specific latent heat. So when you're changing from liquid to gas, you can use liquid to gas. You can use MLV. When you're changing from solid to liquid, you can use MLF. Mass by specific latent heat of fusion, mass by specific latent heat of vaporization. Understand when you need to use which formula, right? Right. So that's basically it there for that. And then we had the using electrical method to determine the specific latent heat of fusion. Basically, what you're going to do here is you're going to heat the ice and allow it to change state to liquid and collect it in the beaker. You measure the mass. So this is basically the steps here. So allow the ice to melt for a fixed period of time. Apply no heat from the circuit without any heating. Record the mass of the water equal M1 without applying heat, right? Just allowing it to melt itself. Now use an electrical heater to melt a similar sample of ice, meaning same mass, for the same period of time and record the mass of water collected. So you can determine how much heat energy you're really using and you're recording the time too. Right? Same period of time. Find the difference in these two masses, M2 minus M1, right? Because you would expect more mass to be melted. Well, yeah, more mass to melt because you're applying heat. So M2 will usually be bigger than M1, right? This gives the mass of the ice that has melted as a result of the energy provided by the heater. The energy provided and the mass of ice as a result are used in the calculation below. So apply this formula here, right? So this is a nice experiment. I'm not sure if you would have carried out this in school, but it's a nice experiment, right? And then we have the equation relating specific latent heat to heat energy. EH is equal to ml, which you would have seen from the graph. E is the heat energy, m is the mass of the substance, and L is the specific latent heat. It could be fusion or vaporization. Right? So we have a little question here to try. Alright, so we have a small block of lead of mass 300 gram is heated until its melting point of 327 degrees Celsius. So that is the melting point. So we have a change in state over here at this temperature. So how much additional energy is required to melt? Well, we know it melting at this temperature, 327 degrees. And they give us the specific latent heat of fusion. So we use heat energy is equal to the mass multiplied by the specific latent heat of fusion. So we will get the heat energy to be equal to the mass, but we have to convert this to kilogram by dividing by 1,000. Right, so 300 divided by 1,000 will be 0.3 kilogram. Right, so 0.3 multiplied by 2.3 times 10 to the power of 4. Notice this is also given in terms of kilogram. Right, so the heat energy will therefore be 2.3 by 10 to the 4, 2.3 by 10 to the 4 times 0.3, 6,900, 900 into 6,900 joules. So that's the answer there. You got that right?